In this lesson, we'll learn how to create an application that responds to user interface events using a variety of event-driven design patterns. Imagine that you need to create an application in which an event on the front panel, like changing the value of a particular control, will trigger corresponding code on the block diagram to execute. For example, notice that each time I change the temperature, degrees Celsius control, the application returns the temperature in degrees Fahrenheit in this indicator. And each time I click the Check Time button, the application returns the current time and date in this indicator. Each time I click the Acquire Data button, the application acquires data and returns the data in this graph indicator. And when I click the Stop button, the application stops. How would you implement this functionality on the block diagram? One way to implement the previous functionality is by constantly polling the values of the controls on the front panel in a loop to check if any control values have changed. Here you can see that this code uses a shift register and a not equal function to determine if this temperature control has changed its value. If it has, then the case structure executes the true case. Here you can see this code continuously checks if the Check Time button is true, and if so, it executes the code in the true case. Similarly, this code continually checks if the Acquire Data button is true, and if so, executes the code in this true case. The false case of all these case structures is empty. However, there are problems with polling. Constantly polling the control values requires CPU usage, and polling can fail to detect changes if the value changes too quickly. In this case, if you click the Acquire Data button 2 times very quickly within one polling loop period, so that its value goes from false to true and back to false very quickly, the diagram might never read the true value because you changed the button value back to false before the block diagram had a chance to read that value. The best way to implement event-driven functionality is to use an event structure instead. Benefits of using event structures include the following: reduces the CPU requirements of the program, simplifies the block diagram code, guarantees that the block diagram can respond to all interactions the user makes, handles all events in the order that they occur, and does not miss any events. Event-driven programming is a method of programming where the program waits on an event to occur before executing the code written to handle that event. An event is an asynchronous notification that something has occurred. Events can originate from the user interface, external I/O, or other parts of the program. Right now, you'll only learn about user interface events, such as value changes of a control. With user interface events, you can design an application so that LabVIEW generates an event each time a user performs a particular action on the front panel. Each time that event occurs on the front panel, the block diagram responds by executing the code you wrote for that event. Let's run this example VI. When I change the value of the temperature control on the front panel, an event occurs that triggers code on the block diagram to convert the temperature to degrees Fahrenheit and display it in this indicator. In the same way, there are other user interface events defined in this VI that trigger other code on the block diagram to execute, such as changing the value of the Check Time button, changing the value of the Acquire button, and changing the value of the Stop button. Now let's turn on Highlight Execution. As you can see, user interface events on the front panel, such as the ones demonstrated here, can trigger the execution of block diagram code that you wrote to handle each event. You should use an event structure to implement event-driven programming. You configure which events you want the event structure to handle. The event structure can have multiple event cases, each of which is a separate event handling routine. When the event structure executes, it waits until one of the configured events occurs, then executes the corresponding case for that event. The event structure completes execution after handling exactly one event. The event selector label indicates which events cause the currently displayed case to execute. You can click it to view the other event cases configured in the event structure. The Event Data node identifies the data that LabVIEW provides when an event occurs. The node provides different data elements in each event case of the event structure, depending on which event you configure that case to handle. For example, the Event Data node for a value changed event includes old value and new value items. You can also resize the Event Data node, and as you can see, you can access the data. When using event structures, you should usually place the event structure inside a while loop. The event structure handles exactly one event per iteration of the while loop. To configure an event structure event case, first select the event structure case you want to configure. Next, right-click and select Edit Events Handled by this case. Then set the source for the event, for example, a particular control on your front panel. Finally, set the event, for example, a value change for that control. Now let me demonstrate how to configure and use events for our example application. Here I have a VI that contains a temperature degree C numeric control, check time button, acquire button, and stop button. First, I'll place down a while loop. Then I'll place down an event structure. You can see a timeout event case that will execute if a specified number of seconds elapses and no events occur. Notice the timeout here. The timeout input specifies the number of milliseconds the event structure will wait for an event before the event structure times out. The default value is -1, which specifies to wait indefinitely for an event to occur. If the event structure times out, it executes the code in this timeout event case. Now, if this event structure waits 1,000 milliseconds and no configured event occurs, this event structure will execute the code in the timeout case. Now I'll configure this event case to respond to a value changed event from the temperature degree C numeric control. Next, I'll create the code to execute when this event occurs. I want my event structure to respond to some other events too, so I will click Add Event Case here. I'll configure this event case to respond to a value changed event from the Check Time button and create the code to execute when this event occurs. Generally, if you're creating an event for a value changed event on a Boolean button with a latching mechanical action, it's best practice to place the Boolean button inside the event case. That way, LabVIEW reads the Boolean button and causes the button to go back to its default value. Now I'll add another event case to handle a value changed event from the Acquire button. Finally, I'll create another event case for a value changed event from my Stop button. Now let's run the VI and test the event handling code. The user interface event handler design pattern consists of an event structure inside a while loop. Each event case of the event structure is configured to handle a UI event, such as a value change of a control on the front panel. Each event case also contains the code to execute each time the event occurs. The user interface event handler design pattern is good for applications where user interface events, like value changes, need to trigger the corresponding event handling code to execute. The event structure handles events in the order they occurred. For this design pattern, the event handling code should be short and quick. Now I'll walk you through the application you'll create in the following exercise using the user interface event handler design pattern. First, I'll run the VI to demonstrate its functionality. As you can see, each of these value change events triggers some block diagram code to execute. Let's take a look at the block diagram. Notice there's a while loop and an event structure. There's also a shift register. This shift register holds the current value of the acquired data. Storing the acquired data in the shift register allows multiple event cases to update and read the current acquisition data. When the user clicks the Generate Stimulus button, this code generates either a 0-volt or 5-volt output, depending on whether the button value is on or off. When the user clicks the Acquired button, this code acquires data and stores the acquisition data in the shift register. When the user clicks the Analyze button, this code reads the acquisition data from the shift register and uses a sub-VI to process the data. When the user clicks the Save Data button, this code reads the acquisition data from the shift register and logs it to a user-specified file. When the user clicks the Clear button, this code clears the acquisition data and graph by passing an empty array to the graph and shift register. Finally, when the user clicks the Exit button, this code passes a true to the condition terminal, which exits the loop and the VI. Here are some caveats and recommendations to remember when using event structures. This state diagram shows the logic of the user interface event handler design pattern. This design pattern waits for an event, and when an event occurs, it executes the corresponding code to handle the event, and then goes back to waiting for an event again. What if you need to handle events for more complicated state diagram logic? The event-driven state machine design pattern combines the user interface event handler design pattern with the flexible transitions of the state machine design pattern. This design pattern allows you to have an event-driven application that can respond to events by executing more flexible state diagram logic. To do this, this design pattern uses a state machine that includes a wait for event state. The purpose of the wait for event state is to wait for an event to occur and then transition to the corresponding state that will handle the event. So the wait for event state contains an event structure, which waits for its configured events. When one of those events occurs, the event structure passes the corresponding next state to the state shift register of the state machine. Let's take a look at an example of an event-driven state machine that implements this state diagram. As you can see here, the first state the state machine executes is the initialized state. Then the initialized state transitions to the wait for event state. The wait for event state then uses the event structure to wait for an event. Let's say the user clicks the Acquire button. The event structure executes the Acquire value changed event case, which tells the state machine to transition to the Acquire state. The Acquire state acquires data and then transitions to the Analyze state. The Analyze state analyzes the data, and if the data exceeds the threshold, the state machine transitions to the Log state. Otherwise, the state machine transitions to the Update UI state. The Log state logs the data to file and then transitions to the Update UI state. The Update UI state passes the acquisition data into the graph indicator and then transitions back to the Wait for Event state. You'll create this VI in the next exercise. LabVIEW includes a template for the event-driven state machine design pattern. You do not need to develop it from scratch. To open this template, navigate to File, Create Project, then click Simple State Machine from the Templates section. You can do this from the Getting Started window, the Project Explorer, or a VI. Now let's take a look at limitations of the event-driven state machine. What would happen if a UI event triggers code that has a duration of 30 seconds? Will the UI remain responsive while that 30-second event handling code executes? Let's observe what happens if one of the states in an event-driven state machine contains code that takes a long time to execute. I'll modify this acquire state by adding a wait function so that the acquire state takes 15 seconds to finish executing. Now I'll run the VI and click the Acquire button. The block diagram code is now stuck in the Acquire state for 15 seconds. In the meantime, notice that my front panel looks unresponsive. A latching Boolean button will stay pressed until the state machine is able to go back to the Wait for Event state, so the event structure can read the button. After 15 seconds, the Acquire state is finished, and the application becomes responsive again. This shows how having a state with a long duration can make the event-driven state machine seem unresponsive. You can use message communication to transfer messages between loops. A message can include data and use the most appropriate data type. For example, every time a user clicks a Process Data button, the application can send a message that includes the data to process to the separate processing loop. In this message communication example, Loop 1 is sending both a message and message data to Loop 2. When the application starts running, Loop 1 sends an initialize string message with a numeric 0 as the corresponding message data. Later, Loop 1 sends a process message along with the message data 100 to process. Then the application needs to log data, so Loop 1 sends a log message along with the log data 50 to write to a file. These messages can get queued up if the receiving loop is busy, so the receiving loop can process the messages in the order received. So in this example, we have seen some common characteristics of message communication. First, we will send our messages and message data to the producer loop and to the consumer loop by using a channel wire. We can make our channel element data type a type definition cluster that contains a string for the message and a variant for the message data. The purpose of the producer loop is to send a message and its message data when an event occurs and to keep the user interface responsive. The producer loop waits for an event to occur using an event structure. Each event sends the message and corresponding message data to the consumer loop. Because the code in the event cases do not do any intensive processing, The event structure in the producer loop is always ready to respond to the next event. The producer-consumer events design pattern. The purpose of the consumer loop is to read and process messages along with their message data. The consumer loop reads messages from the message queue, which then passes to the case structure. The case structure then executes the subdiagram that matches the message. The case structure also uses the variant-to-data function to extract the message data. The subdiagrams of the case structure contain the code necessary to process all of the messages. After the case structure is done processing the message, the consumer loop goes to the next iteration and reads and processes the next message in the message queue. The producer-consumer events design pattern uses message queue VIs, which conveniently provide built-in message and data inputs and outputs. Each message can contain data of an arbitrary type in the message data variant. This is a VI that uses the producer-consumer events design pattern to implement message communication. This producer loop can enqueue a message along with its message data using the enqueue message VI when an event occurs. The consumer loop first dequeues the queued message from the channel using the dequeue message VI, which then passes it to the case structure. The case structure then executes the case that matches the message. The cases of the case structure contain the code necessary to process all of the messages. The case structure also uses the variant-to-data function to extract the message data. For example, the sample rate data in a generate signal case. After the case structure is done processing the message, the consumer loop goes to the next iteration and reads and processes the next message in the queue. Now I'll run the VI. Notice that the code processes messages along with the message data. In summary, the producer loop continuously keeps the UI responsive. The consumer loop executes the code corresponding to the UI events in parallel. These two loops implement message communication using a channel wire. The Channeled Message Handler, CMH template, facilitates multiple sections of code running in parallel and sends data between them. Each section of code represents a task, such as acquiring data, and is designed similarly to the state machine. Because of this design, you can divide each task into states. The CMH template is a version of the producer-consumer design pattern, where the user interface, producer, produces messages, and the tasks, consumers, consume them. However, in the CMH template, you can also have the consumer loop generate messages for itself. This template includes one producer loop and one consumer loop. You can add consumer loops as needed. Open and explore the Channeled Message Handler documentation included in the project to learn how you can modify this template based on your tasks. The Channeled Message Handler design pattern is similar to the Producer-Consumer Events design pattern. Both use channel wires to transfer messages. Both have a producer or event handling loop that streams messages and message data when an event occurs. Both have a consumer or message handling loop that reads and processes the message and message data. The CMH provides better error handling. The CMH handles errors separately from the producer loop and consumer loop. It exits the application if an error occurs in the consumer loop. The CMH also allows you to configure specific errors to ignore in each loop. Here's a summary of what you've learned in this lesson.